Let's look at new applications of the Laplace transform. So let's go into non-homogeneous first-order linear ODEs. We know how to solve this, but let's try to solve it with the Laplace transform as well. So we are setting p to be a constant and q to be depending on x. So we do the Laplace transform. We know how it goes. We get capital Y being Laplace transform of our solution y. We have the y0 popping up. And we can write the Laplace transform of y as a fraction with our constant p plus s at the bottom and qs plus should be the boundary condition y0. Let's try to solve with this with the Laplace transform. So we can easily split it in two trivial fractions, one being something we know how to solve, 1 over p plus s. It's the exponential of minus pt. And the other one might need a second longer. We want to remember that the Laplace of the convolution of two functions is the product of the Laplace transform of the two functions. In this case, this is very useful because we are doing the inverse Laplace. So the inverse of a product is the convolution of the inverses. So we can split qs, the Laplace inverse of qs, convoluted the Laplace inverse of 1 over p plus s. Again, 1 over p plus s, we know how it transforms through Laplace. And the inverse of capital Qs is qt by definition. So we can very easily write the inverse Laplace of this fraction as the convolution of q and exponential of minus pt. Let's look at it all together. We have that yt is equal to the sum of y0 Laplace inverse 1 over ps plus Laplace inverse of q over ps. We have done both Laplace inverses, and we have retrieved a term that is the initial condition times an exponential, plus a term that is an exponential times the right-hand side, the forcing term, as a convolution, so an integral of them. This second term has the problem that it's not always integrable. But this is a very general form. This we can apply all the time. So this is the final solution. Sometimes we will be able to develop the integral and get rid of it. Sometimes you would just stop at this point.